I came across something that completely broke my mind. The headline was that an experiment proving a form of teleportation is real just won 2025 Nobel Prize in Physics. At first, I was completely baffled. It turns out they were talking about a phenomenon called quantum tunneling, where scientists observed an object pass straight through a solid wall on a scale never seen before. This isn't some weird isolated quirk of universe. I learned that it's a fundamental rule that explains everything from how our sun burns to how the phone in my hand works. So I had to ask, how is this impossible feat actually possible? And how did three scientists manage to see it in an object big enough to be visible to the naked eye? A discovery that's changing the future of technology. My gut feeling, my common sense, all my experience told me that this shouldn't happen. If I throw a tennis ball at a wall, it bounces back. It doesn't matter how many times I try, it will never just appear on the other side. The wall is solid, the ball is solid, and it feels like the end of the story. That's the world I see, the one governed by what physicists call classical mechanics. It's reliable, predictable, and for everything my size, it works perfectly fine. But what I had to wrap my head around is that for 100 years, we have known that there is a deeper reality, a layer operating by completely different set of rules. This is the quantum realm. Down at the scale of atoms, reality becomes a wild, fun house of probabilities. In this world, particles can be at many places at once. And for this story, we can essentially pull a disappearing act appearing on the other side of the barrier even without crossing it. For decades, I thought that this weirdness was locked away in that micro world. A single electron might pull off this trick, but a whole object made of billions of them, I would have to say no way. The world of tennis balls and the world of electrons were supposed to have firm, uncrossable border. But what if that border isn't so solid? What if the quantum rules can leak out into things big enough for us to see? That question was the real start of my journey. To understand how something can pass through a barrier it shouldn't be able to, I had to stop thinking of a particle as a tiny solid ball and more of a fuzzy ball. I learned that in quantum mechanics, a particle like an electron is better described as a wave of probability. It sounded complex, but then an analogy made it all click. Imagine being in a huge, pitch black room with a single tiny firefly. You can't see the bug itself, just its faint glow. The light is brightest in one spot, and that's where the firefly probably is. But the glow fades out, creating a huge, faint cloud of light. That cloud is its wave of probability. While it's most likely at the brightest point, there is a tiny chance, a little chance, that it could be anywhere the glow reaches. Now, I pictured a wall in that room, a solid sheet of glass. The firefly is on one side, and so is the most of its probability cloud. But because it's a wave, a tiny, almost invisible piece of that light actually seeps through the glass. The probability wave extends right through the forbidden zone. This means that there is a tiny but real probability that the firefly exists on the other side. If I were to suddenly flip on the lights, the quantum version of observing, I might just find it on the other side. It didn't find a crack or fly over. In one instant, its existence on one side vanished and appeared on the other side. That was my aha moment for understanding the quantum tunneling. It's not about travel, it's a statistical miracle where the universe lets a particle skip the journey. Once the firefly analogy clicked, I realized quantum tunneling wasn't just a thought experiment. It's a process that makes our universe work. What I was calling the glow is what physicists call a wave function, a mathematical map of particles' quantum state. Where a particle's wave function hits a barrier, it fades exponentially as it passes through. But if the barrier is thin enough, the wave function still has a real value on the other side, representing a chance of finding the particle there, even without crossing it. Now, I didn't have to look far enough to see the results. I was stunned to learn that the sun shining above us is powered by this quantum tunneling. Inside sun's core, hydrogen nuclei should repel each other fiercely, like trying to force two positive magnets together. Classically, they don't have enough energy to overcome that repulsion and fuse. The sun shouldn't be able to ignite. But they don't have to go over the energy barrier. They could tunnel through it thanks to quantum weirdness. Two protons can suddenly find themselves on the other side of its own repulsion, close enough to fuse and release enormous amount of energy. Every ray of sunlight is the result of trillions of these tunneling events happening every second. Without it, stars wouldn't shine and we wouldn't be here. And it's not just in space. The device you're watching this video is packed with transistors, and neutron behavior in these microscopic switches is heavily influenced by quantum tunneling. Tunneling isn't some distant concept. I realized it's a core principle driving technology right in my pocket. So I understand that single particles could tunnel, but my big question remained: how big can something be and still act quantum? The old assumption was that for anything made of billions of particles, our normal rules take over. This is the assumption I learned in 2025 Nobel Prize winners in physics, John Clark, Michael H. Deverett, and John M. Martinez, challenged head-on. I read that back in 1984-1985 at UC Berkeley, they set out to build something that would blur the line between the quantum and the classical worlds. They built a millimeter-sized electrical circuit, just big enough to see with the naked eye. They made it from superconductors and cooled it to near absolute zero, which is the key because it shields the circuit from noise that would destroy any quantum effects. The heart of their circuit was a Josephson junction, a tiny insulating gap the current shouldn't be able to cross. This was their wall. In that supercooled, quiet state, something incredible happened. The electrons, the billions of electrons in the circuit started moving in unison, acting like a single giant quantum entity. The team then trapped this macroscopic object in a state where it was stuck, like a ball in a valley with no energy to get over the next hill. The current was flowing, but couldn't push past the junction. And then they saw it. Their instruments showed that entire system, billions of electrons acting it as one, did the impossible. It tunneled through. Without extra energy, the system passed through the barrier, which they detected as sudden appearance of voltage. That was the moment that changed everything for me. It wasn't just one electron. It was a whole electrical system, a macroscopic object exhibiting the weirdest behavior of quantum mechanics. They proved quantum effects aren't just for the atomic scale, but they didn't stop there. They showed that their system had quantized energy levels by nudging it with microwaves and seeing it absorb energy in specific packets, just like an atom. They had effectively created a single giant artificial atom that they could control. So why this changes everything? As I dug deeper, I realized the discovery of macroscopic quantum tunneling didn't just prove a point. It shattered one of the biggest perceived boundaries in physics. The experiments by Clark, Deverett, and Martinez proved the quantum weirdness isn't really about size. It's about how well you can protect a system from outside noise. If you can keep it quiet and cold, it could keep its quantum soul. But I still wondered why this work from mid-80s get a Nobel Prize in 2025? The answer was the final piece of puzzle for me. That experiment, creating a controllable microscopic artificial atom, was the single most important step towards building a quantum computer. Their circuit was the grandfather of modern qubit. A circuit can exist in one state, 0 voltage, and tunnel through another, non-zero voltage, is the physical basis of quantum bit or qubit. Finding that it has distinct energy levels means you can precisely control it. This became the foundation for the conducting qubits that companies like Google and IBM use today. In fact, it blew my mind to learn that John Martinez himself would later lead the Google team to build a quantum computer claiming quantum supremacy. The techniques these scientists pioneered laid the groundwork for what's now called the second quantum revolution. This is our shift from just knowing about quantum world to actively using its strange rules to build things. This Nobel-winning discovery is the direct ancestor of not just quantum computers, but also ultra-precise quantum sensors and unhackable quantum communication. So I started my journey completely baffled by an object passing through a solid wall. What sounded like a sci-fi tagline, now I understand it demonstrated a physical reality. The 2025 Nobel Prize for John Clark, Michael H. Deverett, and John M. Martinez wasn't just a clever experiment. It was for showing that the bizarre, impossible seeing rules of quantum world aren't locked away. They are the fundamental part of our universe, waiting for us to build tools precisely enough to use them. Their work turned simple circuits into artificial atoms, handing us the blueprint for the new generation of technology. What I have learned is that the reality is far stranger and more wonderful than my everyday intuition could ever tell me. The universe, it turns out, is built on a foundation of impossibilities. It really makes me wonder if the building blocks of our technology could literally do the impossible, what other impossibilities are just waiting around the corner for us to discover? Thanks for watching.